There's a moment that happens sometimes late at night when you step outside and look up. The air is still, the stars are out, and for just a second, you feel it, that strange pull between feeling infinitely small and somehow connected to everything at once. It's not fear, exactly. It's not wonder, either. It's something older than both. Something that makes your breath catch, just slightly, as if your body understands something your mind hasn't yet put into words. We spend most of our lives at a very particular size. We move through rooms and streets and buildings. We hold things in our hands. We measure distances in steps, in minutes, in the length of our own arms. The world we touch is the world we understand. But there's another world, vast and silent, that exists all around us, above us, beneath us. A world where our familiar measurements dissolve into something so immense, so incomprehensibly different, that language itself begins to fail. This is the world of the cosmic scale. And once you truly see it, you can never quite look at things the same way again. Scale is something we think we understand. We know that mountains are bigger than houses. We know that ants are smaller than dogs. We live our entire lives making these comparisons, building a mental library of big and small, near and far. But these comparisons only work because everything we're comparing exists within a range our minds can hold. A child's first lesson in scale usually comes from stacking blocks. 1 block, 2 blocks, 10 blocks high before it falls. Simple, tangible, real. But what happens when the numbers stop being countable? What happens when the distances become so large that even our fastest machines, traveling for lifetimes, wouldn't reach their destination? The cosmos doesn't care about our intuitions. It operates on scales that mock our sense of proportion, that turn our carefully constructed understanding of size into something quaint and local, like a map drawn by someone who never left their village. And yet, for thousands of years, humans have tried to measure it anyway. The ancient Sumerians looked up at the night sky and saw geometry. They watched the moon trace its path across the darkness, appearing and disappearing in a rhythm so perfect it could be predicted. They didn't have telescopes or satellites, but they had patience. They had generations of observers who recorded what they saw, who noticed that the heavens moved in circles, in cycles, in patterns that repeated. They began to count, not just days, but the spaces between stars. They invented degrees and divided the circle of the sky into 360 parts, a number that could be divided easily, that made the mathematics of the heavens manageable. They didn't know how far away the stars were, but they knew how to map their positions relative to one another. This was humanity's first attempt at cosmic scale. Not measuring distance, but measuring pattern. Not asking how far, but asking how often, how predictable, how orderly. The Egyptians took it further. They aligned their pyramids with such precision that even today, with all our technology, we're not entirely certain how they achieved it. They understood that the stars weren't scattered randomly, but formed constellations that wheeled overhead with mathematical regularity. They built monuments that would last thousands of years, oriented toward points. Space they could never reach, as if trying to anchor the earth to the heavens. The Greeks began to ask different questions. Eratosthenes, standing in Alexandria around 240 years before the Common Era, noticed something curious. At noon on the summer solstice, the sun shone directly down a well in the city of Syene, far to the south, casting no shadow. But in Alexandria, at exactly the same moment, a vertical stick cast a shadow at an angle of about 7 degrees. He realized what this meant. The earth was curved, and if it was curved, he could measure it, using simple geometry and the distance between the two cities. He calculated the circumference of the earth. His answer was astonishingly close to what we know today. Without leaving the ground, without any instruments beyond a stick and his reasoning, he measured the size of the world. It was one of the first times a human being stepped outside the scale of immediate experience and calculated something vast, something that couldn't be walked across or seen all at once. He made the invisible measurable, but the earth was just the beginning. Aristarchus of Samos took the next step. He looked at the moon and the sun and asked, "How far away are they?" He watched a lunar eclipse and saw the earth's shadow curve across the moon's face. He measured angles and made calculations based on the size of that shadow. His numbers weren't perfect. His tools were crude. But his method was sound. He concluded that the sun was much, much larger than the earth. And if it was larger, and yet appeared so small in the sky, it must be incredibly far away. He proposed something radical for his time, that the earth wasn't the center of everything, that it moved around the sun, not the other way around. Few believed him. It would take nearly 2,000 years before his idea was accepted. But the seed was planted. The cosmos was bigger than it appeared. Much bigger. For centuries, the scale of the universe remained fuzzy. The stars were thought to be fixed to a sphere just beyond the planets, a kind of cosmic ceiling decorated with lights. No one knew what they were made of. No one knew if they were close or distant. The universe had size, certainly, but it was a size that felt containable, finite, almost cozy in its boundaries. Then came the telescope. When Galileo turned his primitive instrument toward Jupiter in 1610, he saw something no human had ever seen before. Tiny points of light moving around the planet. Moons. Other worlds orbiting another world. The universe suddenly had depth. It wasn't a painted backdrop. It was layered. Three-dimensional, filled with objects moving through space at different distances. The cosmic scale started to stretch. Over the following centuries, astronomers measured the distances to planets using parallax. The apparent shift in position of an object when viewed from different locations. They watched Venus cross the face of the sun and used the timing of that transit, observed from different parts of the Earth, to calculate the size of the solar system. The numbers grew. Mars was millions of miles away. Jupiter was hundreds of millions. Saturn even farther. The solar system was vast beyond any earthly comparison, but it was still measurable, still comprehensible, at least in principle. Then came the stars. Friedrich Bessel, in 1838, became the first person to measure the distance to a star other than the sun. He used the same principle of parallax, but on a cosmic scale. As the Earth moved around the Sun, nearby stars appeared to shift slightly against the background of more distant stars. By measuring that tiny shift, a fraction of a degree, he could calculate distance. The star he measured, 61 Cygni, was 600,000 times farther away than the Sun. Let that settle for a moment. Not 600,000 miles, 600,000 times the distance between the Earth and the Sun, a gap so large that light, traveling at over 600 million miles per hour, takes more than 11 years to cross it. Suddenly, miles became inadequate. Kilometers became meaningless. Astronomers invented a new unit, the light year. The distance light travels in 1 year. It's not a measure of time, despite the name. It's a measure of space. So vast that we can only describe it by invoking the fastest thing in the universe moving for an entire orbit around the Sun. And 61 Cygni is close. Cosmically speaking, it's practically next door. The Milky Way galaxy, our island of stars, is about 100,000 light years across. It contains somewhere between 100 billion and 400 billion stars, each one a sun, many with their own planets, their own moons, their own systems. The distances between stars are so immense that if you shrank the Sun down to the size of a grain of sand, the nearest star would be another grain of sand 4 miles away. 4 miles of empty space between grains of sand. And that's just the beginning. Edwin Hubble, working in the 1920s, made a discovery that shattered even this expanded view of the cosmos. He was studying fuzzy patches of light called nebulae. Some astronomers thought they were clouds of gas within our own galaxy. Hubble proved they were entire galaxies, separate islands of billions of stars lying far beyond the Milky Way. The Andromeda Galaxy, the nearest large galaxy to our own, is 2.5 million light years away. Light that reaches us from Andromeda today began its journey when early humans were just learning to use stone tools. We're not seeing Andromeda as it is. We're seeing it as it was, long before recorded history. And it gets stranger. Hubble noticed something else. The galaxies were moving, not randomly, but in a pattern. The farther away a galaxy was, the faster it seemed to be receding from us. The universe wasn't static, it was expanding. Every galaxy was moving away from every other galaxy, like dots on the surface of an inflating balloon. This meant the universe had a history. If everything was moving apart, then at some point in the past, everything must have been closer together. Wind the clock back far enough, and you arrive at a single moment, the beginning. The Big Bang, the cosmic scale, suddenly acquired a fourth dimension time. Not just how far, but how long ago. Not just where things are, but when they were. Today, we know the observable universe is about 93 billion light years across. That's not a typo. 93 billion. Not because the universe is only 13.8 billion years old, but because space itself has been expanding while light travels through it. Light from the most distant objects has been stretched, redshifted, pulled along by the expansion of the cosmos itself. We can see galaxies so far away that their light has been traveling toward us since just a few 100 million years after the Big Bang. We're looking back in time. We're seeing the universe when it was young, when the first stars were igniting, when galaxies were just beginning to form. But here's the unsettling part. We can only see a small fraction of the universe. The observable universe is just the region from which light has had time to reach us. Beyond that boundary, there's more. Possibly infinitely more. Galaxies and stars and planets we will never see, not because they're too faint, but because their light hasn't had time to cross the expanding space between us. We live inside a sphere of visibility, and we can never step outside it. The cosmic scale has an edge, but it's not an edge in space. It's an edge in time and information. Understanding these distances required more than telescopes. It required new ways of thinking about measurement itself. For nearby stars, parallax works. For more distant objects, astronomers look at brightness. Certain types of stars, called Cepheids variables, pulse at rates directly related to their true luminosity. By measuring how bright they appear from Earth and comparing that to how bright they actually are, astronomers can calculate distance. It's like seeing a candle in the dark and knowing it's a candle, not a bonfire, and using that knowledge to figure out how far away it must be. For even more distant objects, there are supernovae, exploding stars that for a brief time shine as brightly as an entire galaxy. Certain types of supernovae have a predictable peak brightness. When one appears in a distant galaxy, it acts as a cosmic measuring stick. And for the most distant objects of all, there's redshift. The expansion of the universe stretches light, shifting it toward the red end of the spectrum. The more red-shifted the light, the farther away and the longer ago. Astronomers have detected galaxies with red shifts so extreme that we're seeing them as they were when the universe was less than 5% of its current age. We've built a ladder of cosmic distance, each rung calibrated against the next, reaching out into the depths of space and time. It's a remarkable achievement, but it's also humbling. Every new rung reveals just how much farther the ladder needs to go. Scale doesn't just affect how we see the universe, it affects how the universe works. Gravity, for instance, is weak. Drop a pen, and it falls to the floor. The entire mass of the Earth pulls it down. But you, with just the muscles in your hand, can pick it up again. You've just overcome the gravitational pull of an entire planet using the chemical energy stored in your body. Gravity only becomes significant when you have truly massive amounts of matter. A planet, a star, a black hole. On cosmic scales, gravity is the dominant force, shaping galaxies, bending light, pulling the universe into vast webs of matter separated by enormous voids. But on small scales, gravity barely matters. Inside an atom, electromagnetic forces are vastly stronger. The nucleus of an atom, held together by the strong nuclear force, could never be bound by gravity alone. The forces that govern the quantum world have nothing to do with the forces that govern the cosmos. This is one of the deepest mysteries in physics. The universe operates by different rules at different scales. The equations that describe atoms don't describe galaxies. The mathematics of quantum mechanics is incompatible with the mathematics of general relativity. We have two separate frameworks for understanding reality, and we don't know how to unite them. It's as if the universe speaks two languages, and we're still searching for a translator. Modern technology exists because we've learned to navigate between these scales. GPS satellites orbit the Earth at about 12,000 miles up, traveling at roughly 8,000 miles per hour. They need to keep incredibly precise time in order to triangulate positions on the ground. But here's the problems. Time runs differently depending on where you are and how fast you're moving. Einstein showed that gravity warps time. Clocks closer to a massive object run slower than clocks farther away. The GPS satellites, being farther from the Earth's center, experience slightly less gravity, so their clocks run faster than clocks on the ground. But they're also moving quickly, and special relativity says that moving clocks run slower. These two effects partially cancel out, but not completely. If engineers didn't account for these relativistic effects, GPS would drift by about 6 miles per day. The system would be useless. But because we understand the cosmic scale, the way gravity and motion warp space-time, we can correct for it. Every time someone navigates using their phone, they're relying on calculations that involve the structure of the universe itself. The same principles apply to particle accelerators, medical imaging, satellite communication, even the semiconductors inside computers. Technology works because we've mapped reality across wildly different scales and figured out how to translate between them. We've learned to think small and think big at the same time. But the cosmic scale isn't just about distance, it's about time. The universe is 13.8 billion years old. The Earth formed about 4.5 billion years ago. Life appeared relatively quickly after that, maybe 3.5 billion years ago. For most of that time, life was simple, single-celled, unremarkable. Complex life, animals, plants, fungi, only appeared in the last 600 million years. Dinosaurs roamed the Earth for about 170 million years and vanished 66 million years ago. Modern humans have existed for maybe 300,000 years. Recorded history covers about 5,000 years. If you compressed the entire history of the universe into a single year, with the Big Bang happening at midnight on January 1st, the Earth wouldn't form until September. Life wouldn't appear until late September. Dinosaurs would show up in mid-December and disappear on December 26th. All of human history, everything we've built, every empire, every war, every discovery, would fit into the last 10 seconds before midnight on December 31st. We are astonishingly new, a blip, a flicker in the dark, and yet, in that flicker, we've managed to look outward and backward, to measure the age of stars and trace the history of galaxies. We've decoded the light from the edge of the observable universe and listened to gravitational waves rippling through space-time from collisions that happened billions of years ago. We've touched, however briefly, the cosmic scale. There's a photograph taken by the Hubble Space Telescope called the Deep Field. Astronomers pointed the telescope at a tiny, empty-looking patch of sky, an area about the size of a grain of sand held at arm's length, and left the shutter open for days. What came back was astonishing. That tiny patch contained thousands of galaxies, not stars. Galaxies, each one containing billions of stars. some of them so far away that their light had been traveling for over 13 billion years. In one of the emptiest looking parts of the sky, there was an entire universe. They did it again, multiple times, pointing at different patches of darkness. Every time, the same result. Thousands of galaxies, everywhere they looked. The implication is staggering. There's nothing special about that patch of sky. It's representative, which means the entire sky is filled with galaxies, stretching out in every direction, farther than we can see, possibly forever. The cosmic scale isn't just large. It might be infinite. Infinity is a strange concept. Mathematically, it's well defined. But physically, experientially, it's impossible to grasp. We can say the word. We can write the symbol. But we can't imagine it. Our minds can't hold it. If the universe is infinite, then everything that can happen does happen. Somewhere. Not just once, but infinitely many times. There would be infinite versions of Earth, infinite versions of you, living out every possible variation of your life. But even if the universe is finite, it's so large that the difference doesn't matter in any practical sense. The observable universe alone contains more stars than grains of sand on all the beaches on Earth, and most of those stars have planets. Many of those planets are in the habitable zone, where liquid water could exist. Some fraction of those likely have life. We're probably not alone. Statistically, the cosmic scale almost guarantees it, but the distances are so vast that we might never know. Two civilizations could exist in the same galaxy, both looking outward, both wondering if anyone else is out there, and never find each other because the space between stars is just too enormous to cross. The cosmic scale connects us to everything and isolates us at the same time. There's a concept in physics called the Planck length. It's the smallest measurable distance in the universe, about 10 to the power of -30, 5 meters, smaller than an atom by a factor that's hard to even comprehend. At this scale, space and time lose their meaning. Quantum fluctuations dominate. The smooth fabric of space-time breaks down into a roiling foam of probabilities. We can't observe the Planck scale directly. It's too small. But theoretically, it's where the laws of physics, as we know them, stop working. It's the bottom rung of reality, the smallest thing that can meaningfully exist. On the other end, there's the observable universe, 93 billion light years across, about 10 to the power of 27 meters. Humans sit almost exactly in the middle. Geometrically speaking, we're closer in size to a galaxy than we are to an atom. We're midway between the smallest and largest scales of reality. It's an odd place to be. Not at the bottom, not at the top. Somewhere in the middle, able to look both inward and outward, able to study quarks and quasars, able to ask questions about both the very small and the very large. Maybe that's not a coincidence. That maybe intelligence arises at this middle scale because it's the only place where the universe can be understood. Too small, and quantum uncertainty makes prediction impossible. Too large, and the distances make interaction impossible. But here, in the middle, patterns emerge. Cause and effect hold. Information can be gathered and processed. We exist at the scale where the universe becomes knowable. but there are limits to what we can know. Light has a maximum speed. Information can't travel faster. This means there's a horizon beyond which we can never see, never communicate, never reach. As the universe expands, that horizon grows, but so does the distance to faraway galaxies. Eventually, galaxies will recede faster than light can travel, not because they're moving through space faster than light, but because space itself is expanding. In the far future, trillions of years from now, the night sky will be nearly empty. Galaxies beyond our local cluster will have receded so far that their light will never reach us. Any civilization arising then would look out and see almost nothing. They might conclude that they live in a small, lonely universe, unaware of the vast cosmos that once surrounded them. The cosmic scale is not just large in space, it's evolving in time. The universe we see today is not the universe that will be seen in the deep future. And then there's the question of what lies beyond the observable universe. We have theories, inflation, but the rapid expansion of space in the first fraction of a second after the Big Bang suggests that the universe is vastly larger than the part we can see. Some models suggest it's infinite. Others propose a multiverse, where our universe is just one bubble in an infinite froth of universes, each with different laws of physics, different constants, different possibilities. These ideas are speculative. We may never be able to test them. But they remind us that the cosmic scale might be even larger than we imagine. That the universe we observe, with all its billions of galaxies, might be a tiny, insignificant speck in something unimaginably greater. It's a strange feeling. Realizing that no matter how much we learn, no matter how far our instruments reach, there will always be more, always something beyond the edge. Always another scale we haven't accessed yet. The ancient Greeks had a word, apeiron. It means the boundless, the infinite, the undefined. It was both a philosophical concept and a cosmological one. They understood, even without telescopes, that the universe might not have edges, that there might be no final boundary, no ultimate limit. Modern science has confirmed their intuition. The cosmos doesn't fit inside our categories. It doesn't end where we expect it to. It keeps going, folding in on itself, expanding, evolving, revealing new layers every time we think we've reached the bottom or the top. The cosmic scale is not just a measurement, it's a reminder that we are part of something so much larger than ourselves that we can barely comprehend it. A reminder that our lives, our planet, our entire history exist within a context so vast that it makes our struggles and triumphs seem both insignificant and miraculous at the same time. We are small, impossibly small, and yet we are here. We are aware. We are able to look outward and understand, at least partially, the immensity of what surrounds us. There's something profound in that, something worth holding on to. Standing outside again, looking up at the stars. They're still there, still distant, still silent, but now, maybe, they feel different, not closer exactly, but more real, more connected. Each one a sun, possibly with planets, possibly with life, separated from us by distances so large that even light takes years to cross them. The cosmic scale is not something we can visit. It's not something we can hold or touch or fully understand. But it's there, all around us, beneath us, above us, woven into the fabric of reality itself. And in some small way, by simply looking up, by asking questions, by refusing to accept the limits of our immediate experience, we touch it. We reach across the dark, and the dark, in its own way, reaches back.